What we're going to be looking at today is constructing a full list of the operations or symmetry operations that can be performed on a given structure. So this mirrors assignment 2 that's posted on Canvas that you should be working on. And what we're going to be looking at today is cyclobutane. And so this molecule, right, it's a four-membered ring. We can abbreviate this or draw this in a simpler form just by drawing a square, which is nice, right? We don't have to rely on any deep artistic skills. And for part one of our video, what we're going to be able to do is look at all of our rotations and all of our reflections. And thankfully, we actually don't have to draw in the hydrogens for part one. So we're only going to be looking at the carbons for part one. And when we're doing any of these operations, if you need to confirm with yourself that these in fact work the way that I'm telling you that they work, I would advise that you draw this molecule or build it in Avogadro, and you can rotate it and see that the hydrogens also work out for all of our operations in part one. Part two, we will need to look at the hydrogens because we're going to see some really weird kind of interactions. And so because our carbons are the only thing that matter for our kind of initial starting point here, we're going to just go ahead and label these 1, 2, 3, and 4. Now, again, the idea of symmetry operations is that if we have this cyclobutane molecule and you were to walk out of the room and I was to move it and set it back down, and you walked back in the room, it would look indistinguishable from its starting point. And so we're going to start by just looking at all of the possible rotations that we have for this chemical structure. So we're going to start with rotations. And there's a lot of them, right? So we're going to go through kind of piece by piece here. So I have my cyclobutane. I have my labels. And again, these labels are just so that we can keep track of this molecule as it undergoes these different symmetry operations. And so we've talked about these different principal rotations or the principal rotation axis for a given structure. And the way that I've drawn this molecule, it's actually sticking straight out of the surface of the drawing surface, right? And this is a C4 axis that we're looking at. And so let's look at what happens as we continually rotate about this C4 axis, right? And so this first rotation is going to be a C4 in this direction. So it's a 90-degree rotation. So by definition, this has to be indistinguishable from my starting drawing, right? This white box that I've drawn must be indistinguishable. So it has four corners. They're pointed in the same directions. You would not be able to tell the difference unless I went about and labeled each of these corners. And now we can see that it is in fact rotated by 90 degrees, right? So this was a C4 rotation. If we carry out another C4 rotation, right, another 90-degree rotation as we're spinning this box, again, it is indistinguishable from where we started until I add my labels. Only now I can see that there's actually a better way of describing this, right? This really wasn't a second C4 operation that occurred. What this was a C2. Right, so let's pick a different color here for our C2 just to make it pop, right? And this is a C2, and what it came from was two sequential C4s. And so anytime we have a C4, you will have one of these C2s. So you can kind of derive that and look at examples for yourself. But essentially, whenever you rotate by 90 degrees and then another 90 degrees, that's the same as if you rotated it by 180 degrees. And so we can take this structure and we can have another C4. Sorry, let me use the right color here so our picture looks nice at the end of the day. Right, and so we have this other C4. We end up with our white box structure here. Let's get back to our nice orange color. 1, 2, 3, and 4. And here we can see that this is in fact another new rotation, or it's another new structure that we've arrived at. This is Yeah, so this is another C4 style rotation. We could also imagine that to get here, we could have done a C4 counterclockwise from where we began, right? So if I was kind of drawing out um, from our starting point, right, we could have gotten here directly by just doing a counterclockwise C4. But because this is a unique operation, we would say this is our second C4 rotation that this molecule actually can do, right, that it can perform. And if we took one final C4 rotation, I'm gonna put this in quotes again because we'll see what this looks like in a second, right, where again, we're just continuing that kind of clockwise rotation. We end up with our 1, 2, 3, and 4, right? We can see that this is in fact our starting point. And so the better way, right, of describing this is actually not by calling it our last C4, but it's by calling it the identity. And so if we're keeping track so far, right, the goal of this assignment and the goal of our kind of next set of practice is to compile a complete list of our symmetry operations. So far, we would say that we had our identity operation. Everything has an identity. We had two different C4 operations that were unique, right? They resulted in a different outcome, meaning our points were kind of shuffled around using these C4 rotations. We also had a C2 rotation, right? And I'm going to leave this in green, and we'll kind of come back to this. And the reason I'm leaving this in green is to remind us that both of these, right, the element was our principal rotation axis. So one of the problems that we worked last week in class asked you to think about what is the difference between a C2 and a C2 prime, and the difference being that the primes generally denote that it is different from our principal rotation axis. And so we had these two different C4s and the C2 that both occurred along the same symmetry element, this axis that's sticking straight out of our drawing surface. And so this is the list as it exists so far. So let's look at our other proper rotations, right? Before we start doing any other kind of fancy manipulations, what other proper rotations do we have? And so we're going to have to move away from our principal rotation axis. So let's draw our molecule or our structure out again. We have 1, 2, 3, and 4. And so what we have actually now is we have a range of different C2 operations that it can occur. So these are no longer our principal rotation axis. The principal rotation axis was that C4 axis that we looked at before. These are now going to be different from our C4 axis. And so the first set of C2 axes that we're going to look at actually cuts this square in half, right? So if we draw this and we connect points 1 to point 3, right, this is a C2 axis. So if we were going to rotate about this C2 axis as drawn, what we would end up with is that 1 and 3 actually didn't move, right? They ended up in the same location. They are located right on this axis. However, 4 and 2 switched places, right? Essentially, we flipped this molecule over like a pancake, rotating about this blue C2. Similarly, right, we could imagine another C2 that's kind of analogous, that goes from 4 to 2. This is a different C2. Right? And if we were going to perform this operation, we end up with a structure where 4 and 2 have not switched places. Right? 4 and 2 have not switched places. They are on this axis of rotation. However, 3 and 1 have. Now, both of these C2 operations are not on our principal rotation axis, so we're going to give them a prime to denote that they are not on our principal rotation axis. And we can see here that these cut through two of the atoms on our square. All right, so now we have these two separate C2 primes, and we can see that these operations, if we're evaluating the total structure, they are, one way we might determine or describe them is kind of like a degenerate operation, meaning they look like the same kind of C2 that's occurring, right? It's a C2 that involves my molecule flipping over, and it goes through two separate corners of my structure. All right, so I'm going to call both of these, I'm going to call this just 2C2 prime, right? So this is 2C2 primes because they are kind of cutting my square in the same way. So let's compare this to yet another C2 operation that we have, having our points 1, 2, 3, and 4. Now we can actually imagine a C2 that cuts my square in half, right? It bisects it. So I have another C2 rotation here that I can draw out. And what we've ended up with is that 1 and 4 have switched places, and 2 and 3 have switched places when we do this C2 rotation. Similarly, right, we can cut right down the middle and do this other C2, right, where 1 and 2 switch places and 3 and 4 switch places. And so again, we kind of have these two other C2 double primes. These don't fit on our principal rotation axis, and they don't cut the molecule, or they don't go through two of the corners of our molecule, right? So that makes this a separate type of C2 operation. It has a different element, right? It has a different axis upon rotation than our previous C2. So let's add these to our growing list of these operations, right? So we had our C4 and our C2. We had two C2 primes, and we had two C2 double primes that we can label for this given structure. And so these are all of our proper rotations, right? We have the rotations about our principal axis that include the identity, and they include the two different C4 operations and the C2 operation. And then we have two different sets of these C2 rotations, right? One that goes from corner to corner on our structure that we can label a C2 prime, and a different type of C2, so our C2 double prime, that actually goes from edge to edge on our structure as we've drawn it. And so these are all of our proper rotations. So let's look at our reflections. And so again, reflections can be pretty tricky to see. And so we want to describe these, and we're going to give a little bit more practice to kind of naming these, whether they are sigma H's or sigma V's, or something new that's called a sigma D for dihedral. And really, when we're in for the purposes of this course, sigma V and sigma D tend to be, you kind of define them retroactively. So let's draw out our structure in a slightly different way that might help us see some of these rotations. So I'm going to have my axes that I'm going to draw, because now that we're talking about reflections, it's easiest to actually use an axis, right, or a set of axes to better describe our molecule. So what I'm going to do is look at, trying to decide on colors here just so we can see these better. If we had a square, I should be able to orient this directly on my axis. That shouldn't be an O. And if this is directly oriented on my axis, right, this is my molecule that I'm looking at. I can still label these 1, 2, 3, and 4. And so now what we're looking at are the reflections that can occur. Now, reflections are not the same as our direct manipulations, which were our proper rotations, right, where I can actually spin the molecule. A reflection is something that is much more theoretical, right? I cannot move a structure where atoms move through each other, which is what we're implying in a reflection. So the simplest case that we're looking at here, and again, my z-axis here is actually that C4 rotational axis. And this is going to be important for how we define our reflections. And so one reflection that we have is actually going to be really, really boring. Right? This plane, kind of as drawn, is a reflection on our xy plane. Right? And this reflection on our xy plane actually results in none of our atoms having moved locations. Right? It essentially cuts all these atoms in half. And so if you think about taking a sphere and you cut it in half and set it down on a mirror, it would still look like a sphere because it's reflected across that surface. And so here we have the sigma xy. And what we can say is that sigma xy is in fact perpendicular to our principal rotation axis C4. When this relationship exists, when our reflection is perpendicular to our principal rotation axis, this gets a sigma h. H you could think of as horizontal, right? That's actually what it does mean. I didn't mean to imply that it wasn't actually horizontal, but we could think of H here as horizontal, meaning if our z-axis is pointing up, and if we look up in our rooms or wherever you're sitting, the floor beneath you is what we would consider to be horizontal. In much the same way, that's the relationship between our principal rotation axis and a horizontal mirror plane, right? If this relationship is true, where our mirror plane is perpendicular to our principal rotation axis, then we have a horizontal mirror plane, the sigma h. Now, for this structure, there's actually two other types of mirror planes that we can draw. Nope, don't want this in green. I want to be consistent, so it's easy to kind of see these pictures. And I really advise you, as you're doing this, to pause this video and try to draw these structures out as we're going so you get comfortable with these different operations. Because again, what we need to do is be comfortable with them when I tell you that they're there. You want to be able to identify your principal rotation axis and then answer discrete questions, right? Does it contain a C2? Things like that. That'll be really important moving forward. All right, so let's draw our molecule back on this structure. Right, so we're putting my carbons along my axes. It doesn't really look like a square, but that's okay. We know that it's supposed to be a square. Right? I didn't get into chemistry because I was an artist. I can draw polygons, right? And I got that going for me, which is nice. Okay, so where are my other mirror planes? So I'm going to try to draw two on here. So one of them is actually our YZ plane of our drawing surface. Right, so this is sigma YZ. And we can see here that sigma YZ contains two atoms, right? And it also contains our principal rotation axis, right? So if we're going to draw this line, that's my principal rotation axis, we can see that that line falls within sigma YZ. So this is one of the two mirror planes I'm going to try to draw. The other one, let's pick another color so we can try to see these and make them distinct. Is sigma xz. And we can see that just kind of like our C2 primes, these two mirror planes are kind of equivalent, meaning they lie directly along my axes. And on top of falling directly along my axes, they contain two atoms. And so here we can see that our mirror planes, so sigma xz and sigma yz, contain my principal rotation axis C4. And if they contain C4, we can call these a sigma V. V, in this case, being vertical. And so both of these are what we would classify as sigma V reflections. Now, they also contain atoms. right? So they contain some atoms, meaning they don't bisect any bonds, right? So these contain atoms, they aren't going through any of our chemical bonds as they're drawn. They're actually going through the nuclei themselves, right? So here we have a sigma H, and we actually have two separate sigma Vs, right? Our XY and YZ are these two different types of sigma Vs. So there's one more case here, and this is going to be kind of the hardest one for us to draw, but let's take a swing at it. So we have one last set of rotations here. Or sorry, not rotations, reflections. Reflections, reflections, reflections. Okay, so here we have our atom, and now I'm going to draw this, and this is going to be kind of the toughest one to see. So hopefully I can make these planes actually distinct. So we can imagine a plane, right, that actually falls between our axes, right? So if I'm trying to draw this out as kind of a plane, it does not fall along our XY axes, right? And so this plane is a mirror plane. If we were going to reflect across this surface, we would see that the ultimate result is that these carbons would switch location and these other carbons would switch location. And so this is one of these potential mirror planes that we can draw, right? So I'll put this as a sigma, and we'll come to define this better here in a second. There's another essentially equivalent mirror plane that bisects my other bond, right? That one might be a little bit hard to see from this kind of drawing, this angle. But again, this bisects or falls in the middle of our XY plane again. And so both of these, right, these two different sigma, so I'm just going to use my colors because it makes it easier until we actually give these a name, right? So both of these sigmas, they still contain my principal rotation axis, right? That z-axis C4. But now they dissect bonds. Dissect or bisect, however you want to describe it, right? These mirror planes actually go through chemical bonds and not the atoms themselves, right? So all of my atoms end up moving here. These get a special label, sigma D. D here being dihedral. And so these dihedral mirror planes actually split a molecule where part of the plane itself does not go through an actual atom. It goes between separate atoms themselves. And so this is a way that we can differentiate the sigma V and the sigma Ds. Right, so we have these two sigma Ds that we can draw for this chemical structure. And so far, right, for this list that we've compiled, this now contains all of our symmetry operations that are proper rotations and our reflections, right? So if we're just going to tally up all proper rotations and our reflections on this list, we would now also have a sigma H, 2 sigma V, and 2 sigma D. All right, so this is now our growing list. And so this is all of the operations that we are currently familiar with, right? We're familiar with sigma H, or we're familiar with rotations, right? These proper rotations, these capital C type rotations. We're familiar with rotate or reflections, so these are the sigmas. We also have inversion, which we're going to talk about in a second. But as I've alluded to, I keep calling these proper rotations. So what is an improper rotation? Right? An improper rotation is actually much trickier to see. These are very, very weird symmetry elements, but they describe, again, a way that we can manipulate the structure that makes it look identical to where we began, right? It makes it look identical to where we began. And so this is going to be the focus of our next video.